Hello, everyone. I'm assuming you guys can hear me and see me okay. My name is Sam. This is the first session here today, and I'm from TradeMasters Workshop Inc., as you can see on the logo over there. We're here today to talk about the theoretical fundamentals of heat pumps. And that means we are going to be dealing with the theoretical part of things, technical part of things, and the fundamental part of things. So let me start by introducing myself. My name is Sam. My partner Chris wanted to be here today, but unfortunately he had previous engagement. Thank you, Burton, for your feedback. I can see it in the chat. So our TradeMasters Workshop is an online institution that helps, I would say, HVAC apprentices to prepare for their licensing exam. And as a part of that, we do deliver instruction on the basics, the fundamentals of the theoretical part of the heat pumps. And from what we hear, I think I am at least under the impression that this part of the apprenticeship training is a vulnerability for the apprentices who are going to write their licensing exam. So it would be a good idea to just go over some of those concepts. But I do also understand that some of you will have a very good understanding of this content, and it might be a little bit rudimentary for you guys. If that's the case, I would just advise to just relax and try to enjoy the content as we go. So what we're going to do today, we are going to try to identify the basic components of a heat pump, and then describe the reversible nature of the heat pump, and then we're going to do some diagnosis, analysis, basic diagnosis on the parts of the heat pump. And to start that, I would like to, as usual, I would like to start with what I would call the refrigeration cycle. Sometimes people call it vapor refrigeration cycle, and review some of the components of this, because we are going to build our understanding of heat pumps on how this basic cycle works. I know it is 100 years old technology, at least that's my understanding of it, approximately 100, if not even more than that. We still use it because it works, because we don't have a very much better, I would say, much feasible alternative to it, but we are starting to use some variations to this technology. So let's start by talking about the four basic components of the refrigeration cycle. If you did your apprenticeship training or any training in this matter, you would know by now that there are four components to this. And the first component is going to be your condenser. The condenser is what is taking the heat and rejecting it to the outdoors, where it is not objectionable. So the job of the condenser is to reject heat to the outdoors, as opposed to the job of the evaporator. Evaporator is responsible for absorbing heat from where the space you're trying to cool. And then you have a compressor, and the job of the compressor is to take a low pressure, low temperature vapor, refrigerant that is, to an output as a high pressure, high temperature vapor. And the reason we do that is because once you have it at higher temperature, I would say much higher temperature, sometimes 30 degrees Fahrenheit, sometimes up to 60 degrees Fahrenheit, compared to the outdoor temperature, this high pressure, high temperature refrigerant is going through these pipes of it's a radiator kind of device, and it is easier now to reject heat to the outdoors because the temperature of the refrigerant is higher than the temperature of the outdoor air. So by losing heat, dropping the temperature and losing heat content, the refrigerant is turning into liquid, and we are sending the liquid to a device that we call a metering device. A metering device has one responsibility. It is going to I would say, meter the flow of refrigerant into the evaporator. We don't want to send too much or too little refrigerant into the evaporator. And metering devices aren't necessarily expansion valves. They could be capillary tubes, they could be fixed orifices. But I think by experience, we've learned that especially thermostatic expansion valves have proven to be the cheapest and most ideal way of metering the flow of liquid refrigerant into the evaporator. So to recoup, we have the condenser to reject heat, we have the evaporator to absorb heat, we have the compressor to change the state of the refrigerant from low pressure, low temperature to high pressure, high temperature, and then the liquid coming from the condenser is metered through a metering device. This is everything that we need to know. Obviously, there are more details to this, and of course, there are always more information to share about this. We know that the evaporators are, that was a very big line. We know the evaporators are indoors for air conditioning because we are removing heat from indoors, and we know our condensers are outdoors because we are rejecting heat to the outdoors, where it is not objectionable. Now, this is great, nice and dandy, but we're going to take this cycle in which the refrigerant flow is, the direction of the refrigerant flow is fixed. So when I say, the refrigerant is flowing in this direction at this point, I mean at all times. So at any time during the operation of the system, the refrigerant is flowing away from the expansion valve to the evaporator, from the evaporator to the compressor, from the compressor to the condenser. This is not going to change for a typical air conditioning unit, or I would say refrigeration also applies in this case. Now, let's have a look at what happens when we try to reverse the cycle, because for a heat pump to operate, what we're going to do is we are going to take, this is very interesting, we're going to take heat from outdoors and pump it to indoors. That's what we're going to do. And how do you do that? Well, there are a couple of ways of doing things. Firstly, I would like you to make a mental note on what you're seeing in front of you here. You're seeing two states of the same mechanical system. Okay, so those are not two different systems. Those are the same exact mechanical systems, but on the right side and on the left side, there are two different operational states of this mechanical system. Let's start with the right side. So we are going to first notice that this says outdoor coil evaporator, and this is indoor coil condenser. Now, this also says outdoor coil condenser, indoor coil evaporator. So the first thing you need to know when you are building your heat pump knowledge based on your understanding of the refrigeration, to drop the terminology of evaporator and condenser. That's the first thing you need to do. And of course, I'm telling you this as someone who has been teaching this for many, many years. So it's a technique to avoid tripping yourself into mistakes. Now, if I call something an outdoor coil, you see, this is an outdoor coil. The same system obviously is not going to change the location of the coil. So this guy here on the right side, of the system is in the outdoor. It's outside of whatever we have installed the system. And the coil that is to the left here and here is always in the indoor. So indoor somewhere. Now, that's the first thing. Secondly, so the first thing is naming the coils as outdoor coil and indoor coil. Okay. Secondly, we need to understand that the direction of the refrigerant flow is going to change or reverse. But it doesn't mean the direction of the flow is going to reverse in the compressor. So for example, when I say the reversing valve, it's also very popular very well-known thing. When I say a reversing valve is reversing the direction of the flow, I'm not saying it is reversing the direction of the flow in the compressor here, okay? It is not. It is, however, changing the flow direction in the other three components of the refrigeration cycle. So you have the outdoor coil, not going to call it a condenser or evaporator at this point, the outdoor coil, the metering device, and the indoor coil. The refrigerant flow direction is going to change in this reverse in these three ones. Why? Well, remember that when we talked about the refrigeration cycle, we said that we take the heat from indoors. Okay, great. So let's take the heat from indoors. Let's say heat is here, and we are sending it to the outdoors. This is called cooling cycle, or cooling in general. On the other hand, if you have heat in the outdoors and you are pumping it to the indoors, what you're doing here is you are, literally speaking, heating the space indoors. So I want you to also now understand that this is the third thing. The first one is we're calling the outdoor coil, indoor coil versus condenser and evaporator. Second thing is the direction of the flow of the refrigerant is reversing not in the compressor, but in the other three components. Number three, we are learning that when we are pumping heat from the outdoors to indoors, we're going to call it heat pump. And when we're dumping the heat from indoors to outdoors, we're going to call it cooling. Okay, let's very quickly have a look at this infamous or famous reversing valve. A reversing valve looks like this. Okay, so this is the same reversing valve anatomy, held by Chris, by the way. I took the picture. And you're going to see, I hope you are going to see that there is a moving part. This is not actually painting enough. So there is a moving part here. I'm trying to paint it or highlight it a little bit. And I'm going to maybe highlight it blue on this side. There you go. So I highlighted blue and I highlighted kind of magenta. And you can see how it is moving within the same cylinder. Okay, so moving left and right within the same cylinder. Why is that? Well, if you look at the movement of this refrigerant flow, it is always coming from the discharge of the compressor to the back entrance of the reversing valve. And for the heating cycle, it is going to the indoor coil, because we have discussed that the discharge of the compressor is high pressure, high temperature. And when it is high pressure, high temperature, the refrigerant gives up heat. So we heat the space indoors. And if you compare it to the cooling cycle, the same refrigerant flow is going also to the back end of the excuse me, the reversing valve, but this time it is directed to the outdoor coil as a high pressure, high temperature refrigerant to give up heat to the outdoors. Right. And now you are obviously seeing the difference in the location of that armature that moves inside the reversing valve. When it is here, as you can see, B and D are open to each other. When it is to the left, C and B are open to each other. So one more time, please note that the direction of the flow in the compressor doesn't change. The compressor is always going to send the refrigerant to the back end of the reversing valve. And you see those three fingers here. The middle finger here, it's always giving back the low temperature, low pressure refrigerant back to the compressor. Middle finger here is always giving it back to the compressor. Now, so that we have done all that, I would like to bring your attention to an opportunity to participate anonymously, and answer a few questions I'm going to ask by following these instructions, if you don't mind. It is obviously not mandatory, but it will help you with pinpointing and thinking about a few things. So if you don't mind going to any web browser on your devices, whether it is a cell phone, whether it is a laptop, a tablet, doesn't matter, and go to the address socrative.com and click on student login, and then type in room name TMWS. So TMWS stands for TradeMasters Workshop. I would probably also put that instruction in the chat in case I move away from this slide. You still have the information there. All right. Now, if you have signed in, you are going to see on your device that you're using a certain question with a certain image attached to it. I will show the question here. I'll just give everyone probably 20 seconds more to be able to maybe sign in or kind of log in as a student. It's anonymous. You don't need to put in any name, any phone number, or anything like that. It will just increase your chances to engage with the content, and it will give me an idea on how well we're progressing with the content. Both Mark and I are trying to keep an eye on the Q&A and the chat in case anyone wants to put in any comments, questions. Feel free. All right. So we have 18 people already signed in to Socrative out of 46 we have watching. Okay. So I am going to move on to discuss the question right now, but this slide is, the information on the slide is also in the chat. Right, so this is the question. It's not a very complicated question, and I think to begin with, and I think that you would look at the image. So reversing valves. Reversing valves in a heat pump always direct refrigerant flow to or back from. So this is your image. This is your image. And what you're doing is you're looking at where the reversing valve directing the flow of the refrigerant. Here, right? It is also sending it out from here. It is from back from here and back from here. So in this case, I'm using the words condenser and evaporator because it is a set function of, I'm going to call it, what should we call this? Are we rejecting heat to the outdoors or rejecting heat to the indoors? I think we're rejecting heat to the outdoors, which makes it a AC, air conditioner. So I got 20 people answered, and I have 50% correct answers here. So let's have a very quick look at what's happening. In the reversing valve, the refrigerant is coming back from the compressor. So I'll just keep everything in one frame. So, and it is sent back to the compressor. So I guess this is good. This is correct anyways. This is correct. And back from the evaporator. So this is your evaporator. In this case, indoor coil evaporator is coming back from the evaporator. And this is going to the condenser. This is going to the condenser or outdoor coil. As you can see, if you have not seen the image, let's just look at it this way. If you didn't see the image, if the image was not there, it would be pretty much, difficult to say what is what. Seeing the image is going to help you to see that the outdoor coil is the condenser, meaning now this is in the cooling mode. All right, so we got 50% correct answers on this one. So the correct answer is going to be all of the above. And all three, A, B, and C, are correct. And if you have any comments or questions, you're welcome to put them in the Q&A section or the chat section there. Right, let's do something else. The reversing valve on a heat pump. So this is your second question, and it is on Socrative. You should see this question also on the device through which you have signed into Socrative. Let's take a minute. My microphone is still working. I'm just giving you some time to think about this. All right. Got 18 people answered. That's very good. So the reversing valve on a heat pump, it looks like this. It has 3 connections. And this is the back entrance that I referred to. The back entrance always comes back, brings back from the compressor, high pressure, high temperature. So this is always bringing back from the compressor. The middle finger here always sends back low pressure, low temperature refrigerant, sends it back to the compressor. So the compressor is sending the refrigerant through the back entrance here, and it is the valve itself is sending the refrigerant back to the compressor to the middle finger here. I hope that is easy to remember, and if you think I'm making any sexual innuendo, you might be right. Throughout years of teaching this topic, I figured out that people remember stuff when there is such innuendo. All right, so the correct answer is actually D, which is 2 inlets and 2 outlets. And how is that working? Well, if you look at the arrows here, I got 67% correct answers, by the way, for this. Thank you for participating and answering. So as you can see, there is 1 inlet here, another inlet here, and then you have 2 outlets. It is the same number of inlets and outlets for cooling cycle and heating cycle. It doesn't matter, the direction might be different, but the numbers of inlets and outlets stay the same. All right. Even if you look at the physical part of this, you can see that. Let's have a look here. You can see that this here is coming back from the compressor, high pressure, high temperature, coming back from the compressor, high pressure, high temperature, and you can always remember that this is too big. Sorry. Let's make it reasonable. So then you can see that this is low temperature, low pressure going back to the compressor. So that's one thing. And if you note, I don't know if you guys see this, but I don't know how clearly you can see my annotation here, but I hope that you see it clearly. This is a loop here. This is a loop, you see? This is where the refrigerant is coming back and going out. That white piece of plastic is the white piece of plastic right here. Right here. The white piece of plastic is telling you that there is a shortcut here. There is a, I would say, current flowing through here to here. As you can see, this is open. So this is communicating with this right now. So this is I'll just use this is communicating here, and this is communicating here, like so. Okay, so this is your direction of flow for the refrigerant, and in this case, obviously, the let's just do this. Refrigerant is going this way. So in either case, cooling or heating doesn't matter. You always have two entrances and two exits to the refrigerant directions. All right. Now, so let's have a look at how things work, though, because if you are going to move that armature inside the valve, then what is actually moving the armature inside the valve? Well, believe it or not, you have something here that is a miniature reverse valve. It's like a relay. If you know how relays work, you give a signal to the relay, and the relay gives a bigger signal. It amplifies a bigger signal to the compressor. Now, same thing work here. That's why we call this a pilot. That is a very bad handwriting. Hold on. I'm gonna write it again. Pilot. So this is your pilot, and it has a solenoid valve. The solenoid valve receives a whatever control signal is, say 24 volts AC. These wires are the control signal wires coming from the control board. And that armature, the small armature here moves, very tiny, very small armature moves, and it directs the pressures of the system. And if we go back to look at what's happening in our valves here, what you're going to notice is, okay, so you probably don't notice it here, but you should remember that the pressure of the system is filling this here. Okay, so the pressure of the system is pushing that armature inside that cylinder, left and right, depends on which side the pressure is directed. If it is directed to the right side here, it is pushing the armature to the left. If the pressure is directed to the left side, it is pushing the armature to the right. And the directing act that I'm referring to is performed by this pilot. This pilot is performing that directing of the refrigerant. Let's get another question. Question number 3. Question number 3 on Socrative. I'll give you 30 seconds. All right. So what do we think? What is the energy source? What is the power that is used to reverse the position in the internal piston, the internal armature? What is the pressure or the power that is moving it? The correct answer is going to be the system pressure. System pressure, as I said, is going to fill in this right side, pushing the armature to the left, or it's going to fill in the left side, pushing the armature to the right. For this one, we got almost 45% correct answers, if you're wondering. Now, let's do another question, question number 4 in Socrative. Let's see how you would fare with this. Another 30 seconds for this question. Um, I think the image is not congruent with the. Sorry, guys, the image is not reflecting the question. So if we just forget about the colors of the image for a moment here. Sorry about that. The image is not reflecting what the question is asking. Actually, the image is more like this. It should be more like this. Sorry about that mistake. So if the refrigerant coming from the compressor is directed to the indoor coil, yes, Jason, I kind of figured that you were not given the fair shot at this. Yeah. All right. So if the refrigerant is the coming high pressure, high temperature refrigerant coming from the compressor is going back to the indoor coil, what are we doing here? Are we heating the space? Are we cooling the space? So that's the question we're asking. Right? Okay. So I think most of you have answered this correctly, and that's very good because this is the heating cycle. Just a very quick review here. During the heating cycle, what is happening is that high pressure, high temperature refrigerant is going indoors. That hot gas is going to the indoor space, not the outdoor space, as opposed to it going to the outdoor in a cooling cycle. I'm pretty sure if I didn't give you the wrong image, you would have answered better. Now, a lot of people ask this question. Okay, I get it. If, for example, we try to heat the indoors, we're bringing heat from outside. But for God's sake, where is this heat coming from? If the temperature outside is, minus 5 degrees Celsius, 20 degrees or 10 degrees Fahrenheit, where is this temperature coming from? Well, to be honest with you, the anything at all that you can touch or see live is a container of heat. There is heat in everything except any substance that is cooled down to negative 273 point something, 72.9 something degrees Celsius, which is the absolute zero, where you have removed every possible bit of heat from that substance. Obviously, negative 273 degrees Celsius is not even close to what we have around us. And it's definitely going to be dangerous and challenging for a lab to drop any substance's temperature to that degree. So, talking about the outdoor air, you can see this is a very nice graph. Not accurate. I don't want you to use this graph for design purposes. This is just for illustration purposes. So if we take the temperature, outdoor temperature, as in degrees Fahrenheit, going from, for example, 0 Fahrenheit to 80 Fahrenheit, and then compare the output of the equipment, our heat pump, as BTU per hour. BTU per hour is the same measurement unit that we use for furnaces. My furnace at home is 75,000 BTUs per hour. It's an old household furnace. So in the same way, your heat pump output will increase. Obviously, there is no doubt about this. Your heat pump output will increase as the outdoor temperature increases. There's no doubt about this. If you have more heat outside, reflected by a higher temperature outside, it means that you are easily taking that heat to the indoors. Now, the temperature drops, obviously, when the temperature drops outside. So you get to a point where the output of your equipment as heat pump is not going to meet the demand of your house or whatever space you're heating. So let's say it's a house. Let's say the house requires 45 degrees, 45,000 BTUs per hour. And now at a 30 degrees, Fahrenheit outside, what you're going to see is that you are dropping below the energy output that you require to keep your house hot or warm. That's what we call a balance point. At that point, you are going to need a little bit of supplemental heat. This is what's applied. I've seen this a lot in Quebec, and it's going to be a lot in Ontario soon. There are so many rebates going on. And what happens is, if your equipment is not able to, on its own, to provide the necessary heat for heating the house, you are going to activate the auxiliary heat. It could be, for example, electric heat, or it could be any fossil fuel heat, for example. And when you add them together, you are going to have enough heat to heat your house. And of course, this line here is representing the heating requirement for the house. So if it is 70 degrees outside, you probably don't need any heat generated in your house. But as the temperature drops outside, your requirement for heat is going to increase, steadily until you reach a point where the amount of heating you need in the house is a little bit more than the amount of heating you can get from your equipment, and that's what we call a balance point. Okay, that's what we call a balance point. Now, I've talked a little bit too much on this one. Any questions? I can see the chat if you have any questions about the balance point. So it's a balance between the amount of heat you need in the house and the amount of heat that your equipment on its own, without auxiliary heat or supplemental heat, can provide you. Okay, so that's the balance point. And it depends on the outdoor temperature. That's not a surprise, of course. Let's do a question, shall we? Question number 5, if you guys don't mind. Question number 5 on Socrative. Air source heat pump means that the condenser, the outdoor coil, I should say, I shouldn't talk about this now because I don't want to give up the answer. I'll explain in a minute. Okay, I see answers are dripping in, so people are thinking about this and providing their answers. I'm going to answer this question, I'm going to refer to a previous diagram we used. We have 28% correct answers. That is understandable because we're looking at things here. So I am going to, explain this right now. All right. So the first option says condensing temperature must be lower than the outdoor air temperature. Now let's just take a step back and see which side are we talking about. We're talking about the right side here because it is a heating function. Okay, that's great. So let's just zoom in here. This is our heating function where the indoor coil is going to be the condenser and the outdoor coil is going to be the evaporator. Okay, so the condensing temperature. Okay, so this is indoor coil is going to be the condensing temperature. We are giving up heat to the indoors. We're giving up heat to the indoors. For this to happen, the condensing temperature should be higher than the indoor temperature, indoor air temperature. If your condensing temperature is not higher than the indoor air temperature, no heat is going to transfer from your indoor coil to the indoor air. That's not going to happen. And your evaporator temperature, your evaporating temperature of the refrigerant should be lower than the outdoor temperature. So if, for example, let's take an example that is known to everyone. We know, 40 degrees Fahrenheit as an evaporator temperature for a certain refrigerant that we're not supposed to use anymore. And if that's the evaporator temperature and the outdoor temperature is not higher than that, if the outdoor temperature is not 60 degrees Fahrenheit, you're not going to absorb any heat from the outdoors. You can't. The outdoor temperature should be higher. So can you use 40 Fahrenheit evaporator temperature? No, because in the winter you're not going to have higher temperatures than that. So if you're doing any heat pump design, your heat pump evaporation temperature should be lower than that, than the outdoor air temperature. Okay, so that's going to be an important point there. So if we go back and check those answers one by one, what we're going to see is that number one, condensing temperature must be lower than that outdoor temperature. So that's irrelevant. This is irrelevant. The outdoor coil is not a condenser in our case. So this is irrelevant. There's no condenser outdoors here, okay? Evaporating temperature must be higher than the outdoor air temperature. Okay. Also, evaporator temperature being higher than the outdoor air temperature means that you cannot transfer heat from the outdoor air to the evaporator. Remember that the heat transfers from where it's more heat to less heat, and it's reflected by a higher temperature to a lower temperature. Okay, so that is not going to be an option for us. Condensing temperature must be lower than the indoor air temperature. Yes, we have a condenser indoors, so indoor coil is a condenser, but how is that condenser going to heat the space around it, the air around it, if the condenser is of lower temperature than the air around it? That's not going to happen. So that leaves us with one valid, option, hopefully, that evaporating temperatures, which is outdoors, okay, outdoors in this case, because it is a heating, it is pumping heat right now to the indoors, must be lower, yes, than the outdoor air temperature. Yes, yes. If this is lower, then the heat from the outdoor air will go to the lower content of heat. That's going to happen. So D is the correct answer in this case. Now, remember what I said. I said that the temperature, the evap temperature should be lower than the outdoor air temperature. And in the winter, we regularly have, 20 degrees Fahrenheit. I mean, that's normal for outdoor air in the winter. So if we have a winter outdoor air temperature is, for example, 25 degrees Fahrenheit, which is very, very common here in around the GTA area, and probably everywhere else is colder in Canada. Wouldn't the humidity that is guaranteed to be in the air then freeze on the coils because the coil is below freezing temperature? Wouldn't that happen? And how the hell is this working for us? Well, the answer is that yes, it does. Yes, the coils are going to grab on those water vapor particles and condense them and then freeze them on the coil so that it's going to become a problem. So what do we do in that case? Okay, we were here and we had this freezing. What we do is something we call a defrost. During a defrost, we actually heat up the outdoor coil like so. You see how we heat up the outdoor coil? We just run the thing in AC mode, in cooling mode, so that the high temperature, high pressure refrigerant goes to the outdoor coil. And we stop the fan outdoors. We stop the fan outdoors. We don't want the fan to be working against our heat coming in. Also, another option that you can have electric heat. Electric heat for defrost is more common than, so what I saw is that electric heat is more common on air conditioning units, and hot gas defrost is more common on commercial defrosts. So this is what's happening, okay? And let's see if we're going to answer question number 6 on Socrative, please. I'm going to give you a minute for this one. I got the right image now. You're right. So 16 participants answered out of 20 who were participating in Socrative. And yes, you're right. The correct answer is A. So when you are doing your defrost, you're technically using the outdoor coil as a condenser, sending hot refrigerant to the outdoors, and you're stopping the fan, because working the fan is going to just cause heat loss for you, meaningless heat loss, that is. So the question is, would there be an issue of piping expansion contraction in defrost cycle? Yes, it would be. But if you, and that's a very good question. Thank you, Sam. So when you are, when it is like -20 outside Fahrenheit outside, and you're heating up those pipes up to 140, yeah, well, you can't do that. But let's say you're sending them to plus 50, 60 degrees Fahrenheit. But here's the thing. Remember, guys, any A coil you have installed in a furnace is exposed to temperatures that go from 40 degrees Fahrenheit to 140, sometimes 160 degrees Fahrenheit. You have those coils, A coils, built like that. So the manufacturers know how to build those coils, whether it is a evaporator or a condenser, doesn't matter. The fundamental structure is the same. They know how to build a coil in a way that the contraction and expansion, thermal contraction and expansion, is not going to cause an extreme situation of a problem. All right. So Let's, why don't we just take another question, if you guys don't mind? This is going to be our last question. This doesn't mean when it starts operating. It means that would be necessary. So actually, the question should say heat pump defrost cycle would be needed when that would be a better wording. Sorry. This is more like a licensing exam question where you're tested for your language proficiency as well as your technical knowledge a little bit and your skills of eliminating the um, options that doesn't necessarily fit. Okay. So we got 21% correct answers on this one. It's obviously very common to be a little bit um, torn between two answers. You probably see two answers. Both are looking good, and you don't know which one to choose from. But again, at TradeMasters, so at TradeMasters Workshop, what we do is we teach students, apprentices, to prepare for the licensing exam, which is 100 multiple choice questions. And there are so many questions where you can see two, I would say, right looking answers, but one of them would be the correct answer. So let's have a look here. Most of you actually chose frost form on the evaporator. Now, I commend you. You can tell that the outdoor coil is the evaporator. That's actually, you should be given a mark for answering D, but unfortunately, that's not correct because, you know, we cannot detect frost we can detect temperature. You know, we can say the temperature of the outdoor coil is below 32 degrees Fahrenheit, above 32 degrees Fahrenheit, or at 32 degrees Fahrenheit, but we cannot in a way detect frost like that, or at least I am not aware of a technology. If you are, please put it in the chat so we all can benefit from that knowledge. So I'm going to say we don't necessarily can detect frost, therefore we cannot initiate frost, or we cannot use, defrost cycle when there is frost. Then there's C, which is the outdoor coil temperature has fallen below or at. Now, that doesn't mean there is frost, because it could be that we just came out of the defrost, and that's not necessarily the case. Or maybe the whole system is not operating. Maybe, there's no call for heating or cooling. So that would be also unnecessary or not good. Frost is formed on the condenser. So if you say that, it means that you have not um, noticed that the condenser is indoors when there is a heat pump function of heating, and heat pump function of cooling doesn't need defrost. The outdoor temperature is obviously too hot that you're requiring heat cooling inside. So that leaves us with only one. So this is also incorrect. That leaves us with only one function. Um, with one function, and that is one option, that is the outdoor coil temperature has fallen to about 31 degrees Fahrenheit, and there is a call for heat. If there is a call for heat, the heat pump system is operating. The outdoor temperature is probably, well, it's below 31, so you started building frost on the outdoor coil. Okay, that's what it means. You started building frost on the outdoor coil, and that's when you are going to have to need the defrosting. So that brings us to the end of the the end of the session here. We have less than 5 minutes to go. If you want to connect with me and ask me anything after, I'm just going to type in my email in the chat. tmws.ca. So that's my email there, sam@tmws.ca. You can visit our website and see. This was a very small part of the training we provide apprentices and candidates of 313A. Licensing exam, and in Ontario we also have 313D licensing exam that goes on, which is a residential air conditioning license. And we do all this training online, and I am so happy to see that also plumbing and HVAC jumped on the wagon here for online training and online sessions. It's definitely more convenient. I'm not saying in person is not better, it is better, but convenience now is the most important thing in our lives. Time is very valuable for us. I hope you guys benefited. I hope you liked, what I presented here. Again, my name is Sam from TradeMasters Workshop Inc., and my email is in the chat. Mark, I'm going to leave things with you. If anyone here wants to, say something or participate. Thank you very much. Thank you, Abdullah. Thank you, Josh. And I hope you guys enjoy the rest of the day. I'm sure the day is packed with nice sessions. Thank you, Saeed. Thank you. Also, thank you, Shane. Thank you, Renfell. Thank you, Rick. Thank you, Burton. Thank you, Robert. Thank you all. And I hope to see you, somewhere in the field. Who knows? Bye-bye.